comprehensive as someone with a computing science background, but normally it does its job. And I think that's why Qiskit is a good example, that like a good package you want to start with. So first of all, what is Qiskit? I'm sure all of you have heard of it. It's an software packaging that's developed by IBM. So because it's a Python package, which means it's very easy to develop on it, you can use all the other existing libraries like NumPy. And if you have experience with this, then writing for loops or define functions or any other more advanced technique are all usable on Qiskit. The second reason is that it's very good documentation. It also has its own quantum computing textbook that you can easily get access on its website. And third is that it has very good community. If you join the Slack community, there are lots of similar mind people. You can ask their questions or share experience, and maybe find someone to work on the same project with you. Fourth is this open source. So for all the documentation you've looked at, you can actually click on it and see how it's written, which I personally find it helpful, because if I want to write a similar expanders library, I can learn how other people's written it. And also when your function doesn't work, when your code broke, you can always refer back to this documentation and see if there is anything wrong with the source. Also, because Qiskit is a fairly new library, you will find some bug in it. And if it's open source, it's easy to actually submit it to the community and let them know that you have experience, like you have some problem with it. And then it has some graphic visualization. It's very easy to plot out your circuit, and for one of its function, it also gives visualization of the qubit, which gives you access within the circuit about how your program's working and if there's anything wrong with it. And last of all is you can run your code both on a simulator or an actual quantum chip. And there are like, I think, more than 10 quantum chips available. Obviously, the more qubit it has, the more crowded it's going to be, because everyone wants to use that. But if your code doesn't require that much high level of computational power, you can always queue up for smaller ones. Also, you can choose which one to queue up to save yourself some time. This is the elements of Qiskit. It looks like a very fancy diagram, but what it is I think there's Greek names of earth, water, air, and fire. So Terra is its foundation, which the majority of the functions you need is that. So you can see Terra has access to the hardware, which means that you can run, so all of the gates that you implemented, it would go through Terra and actually do manipulation on the lower level of a quantum computer. And all the other three ones are more like software expansion to control of your circuit. So here is more of a breakdown of what they all do. When you import packages, you probably need to import some of them, if not all of them. So Terra will go into details later, because this is what you will use a lot. And air is that this is where you run your code on the simulator. And Ignis is, it gives you more of a kind of analyze on your error correction and noise. So if you are very interested in error correction or how the quantum computer is handling your code, then this is the package you want to use. And Aqua is more like a more matured algorithm that have more real-world applications. For example, quantum chemistry and AI or financial optimization, you can all find these demonstrations in Aqua, or if you want to develop them. So this is more of a breakdown of what Terra like entails. So first of all, if you import Qiskit circuits, that's what normally I use, is how you want to construct your circuits. Like you want to add qubits, you want to do gate manipulations. Pulse is if you are more interested in how to simulate single qubits, or like in general, just to simulate pulses to see how they interact. And Transpower, this is one quite interesting one. It helps you to optimize your circuit. Circuit optimization is a very large part of quantum computing, and Transpower have some functions which automatically help you to do it. In my experience, it can do the optimization to a certain level, but it cannot handle a very big circuit. Like you can't just give it a 16 by 16 matrix and ask you to compile a circuit for you. But if you break it down yourself to an extent and then ask Transpower to construct a circuit for you, it can do that. And then if you put different pieces of circuits together and then go through Transpower and ask you to optimize these one for you, it can do that as well. So I think that's quite useful like block of Terra. And then providers, this is more of a space that you send your job like to do it, to visualize it, and tell it where to send your job to. And the quantum info, this is the part that gives you more like kind of analytics of your circuit if you want to gain more information in it. And visualization is like plotting your circuit, see what your cube is doing, these parts. But the main functions you want to use are the first three. Like when it comes to construct your own circuit. So my experience with Qiskit. So obviously, like I said before, I do not have any software development experience. In fact, in my PhD, I do not need to code much either. So I only came across Qiskit this year during its quantum challenge. So quantum challenge has 4 questions. You go through the most basic ones. Like it basically instructs you how to construct your own circuit and then go on to do a BB84 demonstration. And the last one is a circuit optimization, where you have to use the packages we just showed before. And by the end of that challenge, I was quite comfortable with using Qiskit because I think it's very intuitive. So then I was also doing a research project on the application of Grover's algorithm. It was a collaboration with the gravitational wave research, and we want to see how quantum computing would actually speed up gravitational wave research in the future, especially in the data analytics part. So in my part, I use Qiskit to do a proof of principle model of how to construct a template matching oracle, giving an arbitrary number of data and arbitrary number of templates that you want to match. I'm going to go through the 2 main parts in Qiskit, and we're going to see tutorials. So the first one entails is called Circuit Composer. So in this part, you do not need to code at all. It is a click and drop kind of function. So you can just add in qubits and drag gates to your circuit, and then you can run it step by step. And during these step by step, you can also check your qubit state, which is going to show on the block Sophia. I think it's a very intuitive way to understand how quantum computing works and how it manipulates qubit, which is also a very interesting teaching tool. And the next part is what kind of people normally use is the quantum lab part, is where you code yourself. So normally your code would include those 6 steps. So the first one is import packages, which is we shown before, about the ones if you want to do error correction, if you want to visualize it, and you have to import the relevant packaging for it to work. And the second is to initialize your variables. In this part, you would define how many registers you want to use. For example, how many quantum registers and how many classical registers, and how many qubits are there in each quantum register, how many classical bits are there in your classical register. And then the third part is the add gate, which is basically you construct your circuit. And the fourth part is visualize the circuit so you can plot it out. I think this steps, in my experience, is very helpful because when you code, you add gates, sometimes you might just ignore one or two and then your code doesn't work. But it's very difficult to go back and go through it step by step to see, like on the paper, to see which gate you've lost. By visualizing it, you can see the circuit, which gives you extra tool to see if you have ignored anything. And the fifth step is to simulate the experiment, which basically is to send your job to either a high performance simulator or to the quantum chips if you want to see how it was handled in more real life situation. And the last part is visualize the results. So normally when you simulate the experiment, you would give it a customized number of shots, which I think in Qiskit is no more than 8 to 9,000 shots, but normally around, I run my experiment around 2,000 or 1,000 shots, and you can see the probability distribution. And that's what's happening in the sixth step. It normally shows us results in histogram, and you can see the probability distribution to give you the understanding of how your experiment is carrying out. So I'm gonna show you guys. So first of all, if you want to start your quantum experience, this is what it shows. This is what it looks like once you've done, once you've registered yourself with IBM. It's fairly simple. Just Google IBM quantum experience and it will take you directly there. This is what you see. So on the right-hand side is the backends that are available to you, which these are actual quantum chips that you can choose. You can see they've got different number of qubits that you can choose from, and they all got different number of jobs, which you can choose the more free ones, but obviously you don't want to run on the 1 qubit chip. And on the left-hand side, so you have the circuit composer and you have the quantum lab. You have access to both of them, and it's your choice which one you want to use in your relevant project. So I chose Grover's algorithm as the demonstration here. I'm going to show you how it's run in the quantum lab and in the circuit composer. So this is what happens in the circuit composer. As we've shown before, is a click and drop. Okay. So we're going to run through this step by step. So you can see when you start with, you can check your qubit situation. So this is, you can see its relative phase and its probability of what the result is, like what it is. And like both of them. And this is to show it in the block sphere. So this is the starting point. And then this is to add a Hatma gate onto either of them. And then you can check your qubit state again, and you can see now it has changed to a plus state rather than a zero state. And now you can see the representation of the block sphere also changed as well. So this is the NOT gate, and this is a control Z gate. I'm going to show you later how you do this. So this is the end, like after you run all of them, and this is the result of what you will get in the end. And you also have the state vector as well, that you will see the amplitudes of what the possible states are there. And this is the probability. So there is a difference between them, especially sometimes your amplitudes are, well, we all know that the relationship between probability and amplitudes, but sometimes amplitudes will tell you more information than just the probability. So here you can see these are the available gates to you that you can just click and drop at the end of it, and then you will change the circuits, obviously. So this is the 2 qubits, and this is a classical bit that you need to, sorry, 2 classical bits that you will store the measurements of your circuit. And on the right-hand side, you can see the code editor. This is also a very, I personally like this a lot, because sometimes when you construct your circuits, it's a lot easier to do it in the circuit composer because you can see what you're doing. However, if you want to, but circuit composer is good for like a part of your circuit, but it's not very good if you're doing them repetitively, or trying to do some customized like arbitrary function that you want to develop. So what it has on the right-hand side is the codes that you will need in order to construct the same circuits in the quantum lab. So what you can do is copy and paste the code from here and then put it in the quantum lab into your definition, and we'll construct exactly the same circuit here. Right, so I just want to ask if anyone has any question like right now with respect to the circuit composer.
I have a question.
Yeah.
So if I'm not mistaken, Grover's algorithm is a search algorithm, right?
Yes.
So how does a search algorithm works here? I mean, what are the inputs?
So
And
for these ones, these are the tutorial from Qiskit itself. From my experience is they basically mark one state as the desired state rather than actually do. So you have 2 qubits and one of them would be desired, like the marks one. And if the results show it's that's the good state, then they consider this as a demonstration of Grover's algorithm. I know this is not what we want normally, like in a more real world application. And this is actually part of what my project is doing, is trying to do an actual template matching to data, like search if your template matches a certain input rather than just if you can find the marked result.
and how do you correlate your data with the qubit quantum state?
Right. That would be more onto what my research, what my project is doing, rather than the tutorial of Qiskit.
All right.
That's fine. I just don't know if we want to talk about that today.
No, that's fine. I know it's a long talk. Okay, thanks.
Okay, no worries. So just with respect to the kind of technical side, does anyone have more question on the circuit composer? Okay, if not, I'll go on to do the more demonstration on the quantum lab part. So for this part, so before we go on the quantum lab, I think it's important to show you how you can do it on your own laptop. So there are two ways if you want to run Quantum Lab. One of them is through the IBM portal that I just shown you. The other one is actually to install it. So it's fairly easy. Just Google Qiskit and find the relevant documentation. Like here, it shows you step by step how you want to download things and how you want to install it. It's the same as any other Python packages. So therefore, you can run it on your Jupyter notebook, which I personally find it quite helpful because you can run it step by step rather than comparing it with running it on a kind of platform. Right, sorry, just going to find it. Right here. Okay, this is also the tutorial from Qiskit itself rather than the code I wrote. I'm a bit shy to show other people my code because yeah, live demonstration is always a bit hassle. So first of all, this is the part when we say it's in the 6 steps, you want to import the relevant packages. So quantum circuits, this is the one that you need to construct a circuit and execute basically to, as the name says, send it to somewhere to do the job. And air is the relevant part that we're just seeing as the simulator part. And IBM Q is basically you need your accounts to, I think on the simulator, that is not very relevant, but if you want to run an actual quantum chip, you need that. And this is the compiler part. And the visualization, you need it basically just to see your results and your circuits. So here they import NumPy and math as well. This is why I said being a Python package is very useful because you can import other packages as well. And most of the time those really help because as we all know, NumPy is very good at handling vectors or tensor products and stuff. So it's very useful to use that to do like the separation of different registers and qubit operations. I'm just gonna... so this is just show to run through them. So the second part, as with all Python, as they come again to why it is very desirable as a Python package, you can define your functions as you do with normal Python packages. Yeah, another thing is if you want to run on IBM's portal, sometimes it's really slow. Just bear with it. So these ones. So first of all, you define your QC as your quantum circuit for. That means you defined a quantum circuit with 4 qubits, and they are labeled 0, 1, 2, 3, the same as Python always. And this one is just QC dot, and then you put your gate behind it, and that's basically saying you want to do this gate operation on the qubit that was named after the bracket within the brackets. Like for this one is you want to do a Hatma gate on the 3rd qubit and the 4th qubit. And this is a controlled not gate. And for these ones, the first 2 would be the controlled bit and the last one would be the target bit. Sometimes in Qiskit, you can also define multiple controlled gates, like multiple customized controlled gate or customized controlled gate. I think they will show later on because in Grover search, especially in the quantum counting part, you need the controlled Grover's gate, which in this case, you can define, you can change any function you have defined into a gate and then use the relevant functions to make that into the operation controlled by how many qubits you want. So yeah, these ones are all just doing gate operations. Like I said, if you missed 1 or 2 steps in the definition like this, it's very difficult to spot. That's why they did this. So this is the draw part, which is the visualization. As you can see, this shows you clearly what operation is done to which qubit in what order. In this way, if you have missed one or two operations, very easy to spot. And if you want to optimize certain gates operations, it is very easy for you to combine gates and do some operations yourself and then reapply it. So this is the controlled Grover I said before. So this dot two gates and dot control is to help to define a customized controlled gate. And this is the QFT part, the quantum Fourier transform part. As you can see, you can define your swap operations as a function and in a loop. So it can do automatically to all the qubits you want the operation to be performed on, rather than like do the operations yourself one by one. Again, this also just makes me feel why being a Python package is useful, because you can use loops like this to make your operations a lot easier and a lot more like arbitrary. So this is what happens in the end, and you can see this is the controlled gates that it performs, and within each one of them that shows a block is the Grover's algorithm that we defined and as shown previously. And this is when you do the measurements, which is shown by the QC measure. So you basically have to tell us which qubit results go to which classical bit. So this is the execution of your circuit. As you can see, because we run on a simulator, so it is in a very ideal situation. You don't have any amplitudes or any probabilities in the other states. You only have probabilities in the two marked states. And another thing about Qiskit is this is the lowest qubit. So this is the 0th, 1, 2, 3, 4, rather than the other way around. So sometimes you need to get your head around it. By using the relevant actually Python functions, you can interpret your results into a number, and then you can find the angle with respect to the Grover's algorithm in the end. So this is just a brief introduction about how you can customize your functions that you want to implement in your circuits, and how is it more efficient because you can use all these Python functions. Anyone has any question with respect to that part?
So is there any documentation on these on these functions where you can find a list of which ones you can use and what they do?
Yes. So that's why I said Qiskit has very good documentation. So this is, if you just Google Qiskit, it has all of these ones. See the tutorial part, it has circuits, which you can go through them yourself and to see what are the operations you want to have. Or other ones, in other ways, which I personally find very helpful, is the same with all the other coding experience. If you want to use a certain operation, just Google it and add Qiskit, and sometimes it will show its original source file. If it doesn't, like normally it will have a good documentation of saying all the elements with respect to it, but Qiskit is a very new package. So sometimes it only has documentation, but it doesn't have example. So sometimes it's quite difficult to know how to actually implement it. But if you Google it, someone would have used it in some codes with shares, and you can see how to use it.
Also, I wanted to ask, since you said that your results were simulated here, so there wasn't any extra noise, how do you switch between like classical computer simulations and actually working on qubit somewhere in IBM?
Yes, that's the backend. So you see this backend part, like air backend, and it says here this is the name of where the job is executed on, and this is the simulator. And you can see here are the different names that you want. If you want to send your job to any one of them, then basically put these ones into where the simulator is here. And then that would make it possible to run it on actual quantum chip.
Thank you.
Nice. Is there any more questions with respect to this part?
Are you limited by the number of qubits that you have? For example, here you have 9 qubits, I think.
Yeah.
So if you run it on a server with 5 qubits, are you going to be able to simulate it there, or do you need a server with more qubits?
Sorry, I didn't catch your last bit. Would you be able to?
Yeah. So here you have 9 qubits, right?
Yeah.
In this section here. So if you want to simulate this in an actual quantum computer,
Yeah.
you will have to use a server with more than 9 qubits, right?
Yeah.
Or you won't be able to simulate it otherwise.
Yeah, exactly.
Right.
So that's why you can see the ones with more qubits, for example, this 15 one got 700, got 800 jobs before you, so you need to queue for that.
Right, thanks.
And I think in the simulator, it's up to 32 qubits. So even for the simulator, you cannot have as many qubits as you want. Any other questions?
What's the traffic like?
You mean the queuing for the jobs?
Yep.
Well, it's shown here. So yeah, that it has quite a lot right now. So yeah, like you need to choose the right one for your experiment. But I think with educational accounts, if you talk to institution, I think some parts is that you can pay to get access to more quantum chips. But I'm not too familiar with that, so don't quote me. Any other questions? If not, I think I thought that was a just a brief tutorial or demo, like introduction on what Qiskit is. But in general, it is very comprehensive library, and it has. Sorry, just doesn't. Yeah, if you see here, it has these optimization, finance, and chemistry parts, which basically show you the, sorry about my internet, the finished algorithm and relevant topics that you can check on them and to see how they perform. And that's a good starting point if you want to write relevant algorithms yourself. I think that's when I will conclude my talk. Thank you.